I am Dr. P. Saranya, Assistant Professor, PG and Research Department of Mathematics, Sri Sharada College for Women, Autonomous, Salem 16. In this video, we are going to see the topic about inner product spaces. First, we see the definition for inner product spaces. The vector space V over F is said to be an inner product space if there is defined for any two vectors U, V belongs to V, an element U, V in F such that inner product of U, V equal to the complement of V, U, inner product of U, U greater than or equal to 0 and inner product of U, U equal to 0 is and only if U equal to 0, inner product of AU plus BV, W equal to A inner product of U, W plus B inner product of U, W for any U, V, W belongs to capital V and A, B belongs to F. Now we see an example for inner product space. In F power M, defined for U equal to inner product of U1, U2 up to etc. Un and V is equal to inner product of V1, V2 up to etc. Vn. Then inner product of U, V equal to U1 complement of V1 plus up to etc. plus Un complement of Vn. This defines an inner product of F power n. Second one, inner product of U, V equal to 2U1 V1 complement plus U1 V2 complement plus U2 V1 complement plus U2 V2 complement. This defines an inner product on F power 2. Next, we see the definition for norm of V. If small v belongs to capital V, then the length of V or norm of V written as norm V is defined by norm U equal to inner product square root of inner product of U, V. Next, we see the theorem for this topic. If U, V belongs to capital V and A, B belongs to capital F, then inner product of AU plus BV, AU plus BV, which is equal to A complement inner product of U, U plus A, B complement inner product of U, V. And the proof of the theorem is follow from the definition of the property 3. Inner product of AU plus BV, AU plus BV equal to A. Inner product of U, AU plus BV plus B. Inner product of V, AU plus BV. But inner product of U, AU plus BV equal to A complement of inner product of U, U plus B complement of inner product of U plus V and inner product of V, AU plus BV equal to A complement of inner product of V, U plus B complement of inner product of V, V. Therefore, inner product of AU plus BV, AU plus BV equal to A complement U, U plus A B complement inner product of U, V plus A complement B inner product of V, U plus B complement inner product of V, V. Hence the result. Next theorem. Norm of AU equal to modulus of A norm U. Proof. Norm of AU square equal to inner product of AU, AU. This can be written as A complement of inner product of U, U. Since by above lemma, since A complement equal to norm A square and inner product of U, U equal to norm U square. Therefore, norm AU square equal to modulus of A square norm U square taking positive square root which is norm of AU equal to modulus of A norm U. And next we see the another theorem. If U, V belongs to capital V, then modulus of inner product of U, V less than or equal to norm U, norm V. Proof. If U equal to 0, then both inner product of U, V equal to 0 and norm U, norm V equal to 0. So that the result is true here. Case 1. Suppose for the moment that inner product of U, V is real and u which is not equal to 0, we know if u comma v belongs to capital V and a comma b belongs to capital F, then inner product of au plus bv comma au plus bv equal to a complement inner product of u comma u plus a b complement inner product of u comma v plus a complement b inner product of v comma u plus b complement inner product of v comma v. For any real number 1, 0 less than or equal to inner product of 1u plus v comma 1u plus v which is equal to 1 square inner product of u comma u plus 2 inner product of u comma v into 1 plus inner product of v comma v. Let a equal to inner product of u comma u, b equal to inner product of u comma v and c equal to inner product of v comma v. For this, the hypothesis we will get b square less than or equal to ac, that is inner product of u comma v square less than or equal to inner product of u comma u inner product of v comma v. From this, it is immediate that inner product of u comma v less than or equal to norm u norm v. Case 2, if A which is equal to inner product of u comma v is not real, then it certainly is not 0. So that u by A is meaningful. Now, inner product of u by A comma v equal to 1 by A inner product of u comma v, which is equal to 1 by inner product of u comma v inner product of u comma v equal to 1, and it is certainly real. Therefore, by case 1, 1 which is equal to modulus of inner product of u by a comma v less than or equal to norm u by a norm v. Therefore, norm u by a equal to 1 by norm a, 1 by modulus of a norm u, we get 1 less than or equal to norm u norm v by modulus of v. Hence, modulus of A less than or equal to norm u norm v. Putting A equal to inner product of u comma v, we obtain modulus of inner product of u comma v less than or equal to norm u norm v. This is the desired result. Next we see the definition for orthogonal. If u comma v belongs to capital V, then u is said to be orthogonal to V if inner product of u comma v equal to 0. If W is a subspace of V, the orthogonal complement of W. W orthogonal complement is defined by W orthogonal complement equal to set of x belongs to capital V such that inner product of x comma W equal to 0 for all. W belongs to capital W. The set of vectors, set of Vi in capital V is an orthonormal set if each Vi is of length 1. That is, if inner product of Vi comma Vi equal to 1. For if I not equal to j, inner product of Vi comma Vj which is equal to 0. Next we see one theorem. Let V be a finite dimensional inner product space, then V has an orthogonal set as a basis. Proof. Let V be of finite dimension n over f and let V1, V2 up to etc. Vn be a basis of V. Now from this basis, we shall construct an orthogonal set of n vectors. Let U1 equal to V1, U2 equal to V2 minus inner product of V2 comma U1, U1 by norm U1 square. It is a linear space of U2 comma U1. Next U3 equal to V3 minus inner product of V3 comma U2, U2 by norm U square minus inner product of V3 comma U1, U1 by norm U1 square. It is a linear space of U3, U1, U2. Continuing in this way, Ui plus 1 which is equal to Vi plus 1 minus summation j equal to 1 to I. Vi plus j, comma, uj by norm uj square. This is the linear space of ui plus 1, comma, u1 up to etc. ui. Now, inner product of u1, comma, u2 equal to v1 inner product of v1, comma, v2 minus inner product of v2, comma, v1. v1 by norm v1 square which is equal to inner product of V1 comma V2 minus inner product of V2 comma V1 by norm V1 square inner product of V1 comma V1 equal to inner product of V1 comma V2 minus inner product of V2 comma V1 norm V1 square by norm V1 square, which is equal to 0. Inner product of U2 comma U3 equal to V2 minus inner product of V2 comma U1 U1 by norm U1 square comma V3 minus inner product of V3 comma U2 U2 by norm U2 square minus inner product of V3 comma U1 U1 by norm U1 square equal to inner product of V2 comma V3 minus inner product of V3 comma U2 by norm U2 square inner product of U2 comma U2 minus inner product of V3 comma U1 by norm U1 square inner product of V2 comma U1 minus inner product of V2 comma U1 by norm U1 square inner product of U1 comma U3 plus inner product of V2 comma U1 by norm V1 square inner product of V3 comma U2 norm U2 square inner product of U1 comma U2 plus inner product of V2 comma U1 by norm U1 square inner product of V3 comma U1 by norm U1 square inner product of U1 comma U1 equal to inner product of V2 comma V3 minus inner product of V3 comma V2 minus inner product of V2 comma U1 U1 by norm U1 square by norm U1 square into inner product of U2 comma V2 minus inner product of V2 comma U1 U1 by norm U1 square minus V3 inner product of V3 comma U1 inner product of V2 comma U1 by norm U1 square, which is equal to inner product of U2 comma V3 minus inner product of U3 comma V2 by norm U2 square minus inner product of V3 comma U1 inner product of V2 comma U1 by norm U1 square norm U2 square minus inner product of V2 comma U2 minus inner product of V2 comma U1 inner product of V2 comma U1 by norm U1 square minus inner product of V3 comma U1 inner product of V1 comma U1 by norm U1 square equal to inner product of U2 comma V3 minus inner product of V3 comma V2 plus inner product of V3 comma U1 inner product of V2 comma U1 by norm U1 square minus inner product of V3 comma U1 inner product of V2 comma U1 by norm U1 square, which is equal to 0. Therefore, U1, U2 up to etc. Un are orthogonal. W1 equal to U1 by norm U1, W2 equal to U2 by norm U2 up to etc. Wn equal to Un by norm Un. Therefore, set of W1, W2 up to etc. Wn is orthogonal set which is linearly independent and dimension of V which is equal to number of elements in this set. Therefore, it forms basis. Thank you.